Right? So you don't have protocols like ARP or ESIS. IP requires that you have layer 2 point-to-point identities because it needs point-to-point identities. You know, that's what it speaks, that's what an IP address means. And so it has binding operations to set those up. You don't get them in CCN. So those are two simplifications. There's a complication. You have to handle multi-access interfaces, broadcast interfaces. And the canonical problem on a multi-access interface is a success disaster. You ask for some piece of data, and 100 guys have that piece of data, and they all try and give it to you. And they were synchronized by your question, so they all try to give it to you at the same time. It's called an ACK implosion. The MAC level protocol will resolve the contention so that they don't put their bits on at exactly the same time, but it's a huge traffic burst. And it's also doing nasty things to the MAC. It's driving it into a deep congestion state. So you don't want that to happen. Long ago, when we were doing multicast protocols, it became clear how to do protocols to avoid that. It's called a suppression mechanism. So you're broadcasting the question. You want to do the transport equivalent of CSMA, which is you want to randomize the responses over time and have the responders broadcast so all of the potential responders can hear the first responder, and they then turn off and they say, okay, I don't need to respond because somebody else already did. So rather than having everybody respond instantaneously, you want to spread them out. You may have to spread them, if there's potentially a lot, you could spread them out over a long period of time because of the birthday problem. It says that if you really want to make sure that only one responds, then the time interval has to go like the square of the number of potential responders. So if you've got 10 guys, you've got to wait for 100 time units in order to not have them conflict, not have two in the same response interval. That's pretty grim. To get around the birthday problem, what you try and do is partition the responders. So you make some rule for who should respond first, so that within the partition, the numbers are small, and so you don't have the n squared doesn't bite you. In a partition, if you got one guy, it's a big win, because 1 squared is 1. So there's a simple prioritization rule for CCN. If you created the content, you're very high priority to respond. You're the guy who made it, right? You should get to answer questions about it. If you didn't create it, but you learned it off of some other wire, hypothesis is it wasn't created on this net, and if it was, the guy who created it will respond. If you learned it from some other wire, then your second priority to respond. And so you're a router, you got the data via some other source, or you learned it in another environment and you brought it here. So you can source it onto the net. Then the lowest priority is if you learned it on this wire, your lowest priority to respond because many other people learned it on the same wire. And so you should randomize over a big interval. With that priority rule, you can do a simple suppression where if the content is being created on the net or being sourced on the net, there's no delay at all, right? The creator just immediately sends you the data. If it's being gatewayed from some other net, the gateway responds after a very small delay with the content. It's just making sure that the creator's not there. If it was learned on this net, but the original creator of the gateway went away, then anybody who's got a copy will give it to you, but after a substantially longer delay. But you only do that for the first time. We've got this name structure, and it can remember stuff about this name prefix. So you remember in the prefix, if you responded last time, if you were the one that won the suppression game. And if you won last time, then you get to send immediately next time. And you get to do that for n many trials. So you amortize the cost of doing the suppression by essentially doing an election once via a contention mechanism. And then after that, you use that election for some period of time, until you run out of data or it's time to run a new election. And at that point, you run a new election. therefore deal with this broadcast interface as if it were a point-to-point interface. You don't have to deal with contention issues because you've got some memory. Now I want to say some heretical things about QoS. If you look at where there are quality of problems in the current internet, they're not distributed throughout the internet. I'm having a phone call, Skype call, and I'm losing big. It's not because I'm losing a little bit at 1,000 points along the internet. I'm losing at one point in general, right? There's some exchange point, peering point, choke point, the return path, the tail coming out to me, the tail going to the other participant. There's some fast to slow transition where a lot of traffic is piling up and stuff is getting lost. Because the only place you get queues are where you get a fast to slow transition. And there aren't many of those. That doesn't do you any good. I mean, you can know that, but it doesn't help you fix the problem. The call still sucks. And it's because the communication model in IP is this sort of action at a distance model. We want the abstraction that you have a single wire between the source and the destination. And congestion is a property of that virtual wire. And its components, its individual elements, they're not visible to the endpoints. There's nothing you can say about it. I mean, there's tools that you could run, path care, traceroute, things that will tell you what's going on there, but they still don't help you. You might be able to identify the problem, but you're not going to be able to get anybody to fix it. So for IP, the observation that congestion tends to be localized, it's properties of the engineering of the infrastructure, that doesn't help you. That localized congestion is generally half the problem. There's another half the problem that comes from IP's unidirectional model. And my example of this congestion is my son's just completely addicted to computer games, right? He never sleeps. He grabs food from the kitchen, goes up to his room, and he's just continuously immersed in these games. And they send huge volumes of data over our internet link, which, because I live in the US, is a slow link. My wife and I are trying to get work done over that link, and we have to compete with his goddamn gaming traffic. And we can't tell our ISP that our work traffic is more important than his gaming traffic, right? It's because the queues are in the direction of the ISP to us, right? But the interest, the value of the data in those queues is in the us to ISP direction. And there isn't a channel that goes from us to the ISP. There's channels that go from us to the ultimate destination and back again. But there isn't a local communication channel where I could say, I'm the guy that pays the bill, send those bits first, or send his bits last, right? It's not a way to express that. So I tried to make the point earlier that in CCN, all communication is local, and it's in the CCN model, the communication is local. You're talking to an upstream, and it's a bidirectional communication. You send an interest, it sends a data. Right? Some of the annotation that goes in the interest says, this data is more important to me than anything else I've asked you for. Right? When you get data that matches this interest, and you have a choice of 10 things to send this first. Right? So there's an explicitly, because the upstream agent is in the protocol. It's the thing that you're sending your interest to. Right? You also communicate your utilities to it. And because there's this flow balanced interest data communication, it can react to that loop. It can say, okay, I'm pulling the stuff out of the content store and I don't care about the order, but my customer told me he cares about the order, so that's the way that I'm going to pull it out. So the local communication gives you a channel to remediate this problem, the lack of the detailed control over the bottleneck link, because both ends are explicitly modeled. It's not action at a distance, it's local action. And each of the links is treated differently, right? So I have a business agreement with my ISP. They have a different business agreement with their ISP. And over that link, they have their own utilities. Their utilities can be, I sold my customers telephony service and deliver on that telephony service all the telephony traffic, which I rate limit and admission control. I want you to service that first. That's their agreement. They don't have to have the same agreement that I have, because it's a different conversation. And so because it's local and because it's pairwise, it can reflect those local agreements. It's not a one-size-fits-all, and it's not an action at a distance. And the part of the problems that have to deal with queues, there are no queues. So you can just punt those. But this last line is saying what I just said about ISP agreements. Whenever you're aggregating, aggregates can create problems. And so you have to deal with how you want to service the aggregate. And you do that in the context of a business agreement. Either customer-provider business agreement or provider-to-provider business agreement. And if you model the individual links, that's easy to do. Boy, I'm going real slow. I want to talk about routing. Routing's recently become an area of active research, and there's just very exciting things that are happening there. Very scalable, locally controlled, local model routing. The most popular ones are various ways of doing small worlds, either explicit small worlds, hidden metric space small world routing, or more explicit small worlds, Kleinberg's hyperbolic routing, where you can use approximate, incomplete local information, but still get very good routes with very low stretch factors. So this potentially has great scaling. You can have lots of information, but you mostly don't need to know it. You just need to know the stuff that is around you, and it doesn't require summarization. There are more viral models, things that handle very high degrees of mobility, where you're doing stuff that's based on either gradient models, stuff that you should avoid, or percolation models, random walks with learning, so that you can find hubs and good distribution centers. It's all very cool. I think any of it applies to CCN as well as to IP. We're semantically pretty equivalent. It's generally easier to do in CCN than IP for a few reasons that I tried to put here. You don't require convergence in CCN because it's not possible for things to loop. Right? So you don't need a stable topology. You don't need short times to a stable topology, because those exist to prevent looping, and you don't care about looping. The fact that you've got multi-destinations means that you don't need perfect state. So IP requires a certain minimum amount of state because you have to distribute packets along its spanning tree. You can't send packets along the spanning tree and somewhere else, because that might cause a loop, and loops really rapidly take down your network. And you can't send your packets somewhere other than along the spanning tree, because that might cause a black hole. You might send them to somebody who doesn't know where they go. So in IP, at every node, you have to have perfect information. You can't approximate it. CCN, the semantics of a fib entry is this node might have information about the prefix, or information that matches this prefix might be out that face. It's approximate to begin with, and it can be multiple faces. And you can take all of the state and turn it into summarized approximation state, as long as the errors that you're making are false positives. You can send the data anywhere, not just waste bandwidth, as long as one of the places that you send it is the place you should have sent it. Right? So in specific, if you want to code your routing tables as a Bloom filter, works perfectly. Right? Because Bloom filters only have false positives, they don't have false negatives. Right? You're never going to fail to send the data where it should go, but you may, because you compress the state, send it some places where it shouldn't go. That's okay, it'll get discarded because they don't have the data. And you get that out of the multi-point model, sort of for free. It's a consequence of having multi-point delivery. But it means that you can make some, if you care about state and state concentration, you can do explicit state versus bandwidth trade-offs. You can say, oh, I can compress the bejesus out of the state, And all that happens is some fraction of the packets are going to get flooded. They're going to go places where they shouldn't and get discarded. And lastly, if you look at the transport protocol used by routing, it's always a flooding diffusion-based protocol. It has to be, because it's the protocol that's used to create topology, and so it can't rest on topology, right? There would be a recursion problem there. So you have to make routing out of something that doesn't depend on routing. And flooding's all we know that doesn't depend on routing. You can decide it locally, you can implement it locally, it only depends on the information. That means that CCN lets you implement routing protocols directly in the CCN protocol, because its model is what the routing protocols would like to use. So if you want to try any of those things, I'd suggest, hey, do it in CCN. Right? It's just a great discovery vehicle, and if you do it, you get infrastructure protection for free because all the information is secured. You know, it's all signed. I'm not going to talk about any of those. I want to encourage, let's deploy CCN right now today, and you can do that. It's universal middleware model. You want to deploy it over the existing IP routing. Like I said, longest match lookups, it's semantically compatible. It expects the same sort of things that IP expects. If you can do that, if you can dump CCN information into normal internet routing, then you really can deploy it today. And if you can do that, might give you some intuitions on scaling. It really is just the same as IP routing, should have the same scaling properties. So in order to describe that, I need to describe how routing works, because it's black art to many people, probably not to you, but I'll describe it anyway. So I'm just describing link state routing because the other one doesn't really work. Link state, we have nodes that announce their existence via local broadcasts. Across every link they've got, they send out a hello that just says, I exist. So B sends out of each of its links, hello, I'm B. A node that hears that learns that it's adjacent to B, that B can talk to it. So when C hears B's hello, which is local communication on that one link, when C hears it, it floods via a link state announcement what's called an adjacency. So it tells the whole world that there's a unidirectional path from B to C. Same thing happens in the other direction. Okay, so C is sending a hello, B floods an adjacency, the whole world learns there's a unidirectional path in the other way, C to B. As soon as the world learns that there's a path both directions, right, this is flooded, so it goes to everybody. So when everybody learns that there's a path from C to B and from B to C, they make a map of the network that includes a link from C to B. For ISIS and OSPF, we require bidirectional connectivity, right? So you have to hear an announcement from each direction, and that causes you to put a link in your map. Every node in link state routing is building a map of the network, right? So everybody's playing this game. Pretty soon you're going to get a map of all the connectivity, right? So you're going to end up with this structure that's drawn here. So that's one part of link state routing. It's the internal part. Each node is creating a map of the entire topology. And it's doing it via these flooded LSAs, which in turn are coming out of the local hellos, which give you the adjacencies. So everybody has this map. The other part is using it. So some external agent, something not part of the cloud, is saying, I'm adjacent to B, and anything that's prefix 192.168, I can reach it. Right? So there's some outside world entity, another routing protocol in the same box, BGP, another version of the IGP. It supplies a prefix that says, at this node, that prefix is reachable. Right? So B takes that prefix and it floods it throughout its network and saying, the prefix 192.168 is reachable via B. You can send to me if you want to get to that. So that's using the map. And again, this is flooded. Everybody learns it. The prefix announcements aren't protocol specific, and they're not topology specific, right? They're information that you want attached to nodes. It can be an IP4 prefix. It can be an IP6 prefix. It can be a time of day. It can be an MPLS label. You really don't care. It's some information that you want associated with a point in the topology. And in the process of moving the protocols from IP4 to IP6, and then trying to put in MPLS and traffic engineering extensions, both OSPF and ISIS really generalize the mechanism for what you can announce at a node, because there were lots of different things they wanted to be able to announce. Prefixes in multiple protocol families, characteristics of links, all of those things could be distributed. They could be encoded in what's called a TLV, type length value. You get to choose the types arbitrarily. You say how many bytes of data there is, a code for the type, how many bytes of data, and then that many bytes of opaque data. And that can be flooded throughout the entire topology. It's attached to a particular node that originates it. So model is you have CCN content repositories that have certain prefixes they handle. They learn about that via internal CCN protocols called registrations. There's a registration agent that talks to routing, to a border router, and says, these content labels are available next to you. Right. So adjacent to B is some set of name prefixes, CCN prefixes. B takes those prefixes, floods them via the IGP flooding mechanism, the TLV mechanism, floods them throughout the topology. Routers that don't speak CCN, the guys that are only single line, they discard the information. They say, it doesn't apply to me. Guys that do speak CCN, they use it to build a fib. So you hear an announcement from A about the prefixes it handles. This is the fib that you build from those announcements. You hear an announcement from B about the prefixes it handles. It makes that fib entry. It doesn't matter how you learn it. Right? You're getting the labels bound to points in the topology via the IGP flooding mechanism. You're using it as a transport. You construct a fib because you know the topology and you know where the labels are. You find the closest CCN capable entity in the direction of the prefix, and that's what you put in the fib. Right? So here, the closest CCN capable entities are the originators, A and B. If you upgrade C so it speaks CCN, all those fib entries turn into Cs, right? Because the way that you would get to A or B via a CCN capable path is via C. So you can dump CCN prefixes because they're semantically compatible with IP and because the routing protocols are sufficiently general. You can jump them straight into your existing IGPs. You can dump them straight into BGP the same way. It had the same TLV mechanism for the same reason. It's unfortunately not a link state protocol. It's a modified distance vector protocol, and it tends to hide a lot of information. So I'm not sure that you want to do it that way. What we're doing currently in CCN is using the DNS in order to handle the interdomain case. And I'm not going to talk about that, but can talk about it offline. I want to talk a little bit about problems with the IP routing model that you don't have with the CCN model. So I did this picture about how the data is summarized, reduce it to just the node link diagram. Right. So these were the subnets, the net, the foreign nets. That's the connectivity. Problem is, it's got a lot of double edges. It's got a lot of loops. And IP can't deal with that. So you have to impose a topology on that. After we've done the routing computation, we end up with a spanning tree. So a bunch of the edges have to vanish. They have to go away. Even though that's capacity that we could send bits over, we can't use it. We're talking about a topology that has to span the whole world, and there has to be a lot of consistency in that topology. Right? There's certain levels of churn where you can't send data if the topology is still converging. And core parts of the topology, if they change, it can take a long time to reconverge, to reestablish that topology. So there's lots of times when you may not be able to send data. And those times can be triggered by very small things. A couple of years ago, an ISP in India, a really tiny ISDN ISP in India, misconfigured their prefixes. And they were injecting via BGP 100,000 withdrawals, announced withdrawals an hour. And that caused BGP boxes all over the world to fall over. Right? Cisco's just couldn't handle that rate. TCP could move the bits, but the BGP and the mesh topology that's implied by BGP, it just couldn't handle that traffic rate. BGP router falls over, then you lose the high level, the tier 1 adjacencies, right? So this churn at the far edge of the network is almost inconsequential. It turns into churn in the core of the network, and it took down the internet. Right? There were large parts of the Pacific Rim that weren't reachable, and they weren't reachable for a couple of days. Cisco sent out an emergency patch. People were filtering out. They identified who was doing this. They were filtering out the traffic, but they had to do that manually. And because we require this topology to communicate, we're dead in the water. So there are global effects for local actions. And it doesn't have to be a big player's local action. It could be anybody's local action. And that's it. You get global constraints on the forwarding because you have to be on the spanning tree. And for the intermediate guys, they don't get a choice. Right? Because in IP there's only one path between any 2 points. When you get a packet to a non-local destination address, you have to forward it. It doesn't matter if you look at it and you say, oh, I don't want to handle this, right? That's not my customer, or I don't trust this packet, or I'm really at my quota. You are on the path, right? If you got it, somebody thought that you were on the only way to get between point A and point B. And if you throw the packet away, then you've made a black hole. Those two nodes can't communicate. So you end up, because you have to be part of this global forwarding structure, the single spanning tree, you have global constraints on your local routing decision. If you do CCN, you don't need topology. At best, it's a hint. It saves you some bandwidth. Right? You can use any or all your links, and you can use them all the time. You don't need it because the content model suppresses duplicates. There's nothing that can loop. Data gets extinguished immediately if it goes around a loop. There's something called a nonce. There's an identifier that goes in the interest. If they go around a loop, they get extinguished. The data bandwidth is going to be a theoretical min, right? You get the data from the closest point. If you do that by flooding interests, there's going to be some off-path, off-closest point copies that get sent to you and they get extinguished because they're duplicates. If you have topology, then you don't send those off-path interests. The amount of win that you get from doing that is a really small factor. It's some fraction of the average degree times the diameter of the net. Those copies would tend to go off and then remerge again unless the data is really in disjoint places. And so what you win is those little splits. And if you actually compute it, it's a tiny number. So you actually get CCN to work best if it's got Chroming topology, approximate topology, and you do something that we call performance-based interest expression. I've only got 10 minutes. So. And I'm losing my mic? Okay. I want to go briefly into transport. It's the last big issue, and I think I can skip the rest of the slides. We've got this tree-based content model, and you're asking for things an item at a time, right? How do you get big stuff? How do you say what you want? That's the fundamental problem of transport. It's easy in a stream-oriented transport because basically you're enumerating a byte stream, right? And a line is totally ordered, right? So if you say what you've got, you can say the mark between what you've got, that's what you want is everything after that mark. And that's what TCP does. That's what a TCP sequence number is. So there's some point that an ACK identifies that's everything that you've got, everything after the ACK, all the bytes higher in sequence order, are stuff that you want. And there's another parameter called the window that's how much you allow to be in transit. So how many of those bytes the sender is allowed to send. It's a really compact state. It's really easy to robustly move data. How do you do the same thing with this tree-structured CCN namespace? Well, you take advantage of the fact that the one data structure, in addition to a line, that you can totally order as a tree. You can't totally order a graph. You can't totally order any two-dimensional or higher structure, but you can totally order a tree. In fact, many different ways. We order it in pre-order, lexicographic order. And that means that these names have a total ordering. Therefore, I can say what I want relative to what I have. And that specifies a particular path through the tree. And I put the conventions down here. The tree is lexically ordered. If you don't give a relationship, what you're asking for is the leftmost child going down the tree. So you're going to follow the branch. I probably have this on a picture, and I should do the picture. So if I give that name, slides from a talk, and I want to ask for the highest version, but I don't know what the highest version is. Right? So I ask for the base name of the talk, not including the version number, and I ask for the rightmost child of that base name. Version numbers are ascending integers, so the rightmost child is the highest version. That's the application convention. So asking for the rightmost child gives me the most recent version, and I don't need to know what it is. And then from the rightmost child, the default convention is follow down the leftmost child. So its leftmost child is block 0 in that piece of content. Right? So that name is going to give me the first block of the most recent version. And I don't have to know anything more than the base name. If I want the next version, it's pub/sub, I'm trying to find that a new version has been created. So I asked for the version after version 2. So it's the rightmost sibling of version 2. There isn't one. And you go back, if you talk to something that's authoritative, a repository for that content, it's going to give you back a NAC that says, doesn't exist yet. I know, and it doesn't exist yet. If you don't get to an authoritative repository, it's going to time out. If I've got chunk S1 and I want some chunk after it, so it's the TCP example, I've got everything S1 and before, and I want something after it, I ask for that name. I give the name of the most recent thing I got, and that implicitly, because of the resolution rules, is the next thing, anything afterwards. So the names are what you use for transport state. Basically, you get a packet in the default case, and you turn the name in that packet into your next interest. And that interest is asking for the thing after what you've got. Content storage. So there's roughly 10 million people that read the New York Times online in the US. And they all pull a copy from the nytimes.com. It's not Akamai's because NY Times wants to tell its advertisers exactly how many people read it. How would you do that with CCN? Well, said the model is a sort of recursive model. Client announces its interest. The interest percolates back to NY Times because nobody along the path has it. NY Times sends the data. As it's going back down to the client, it's remembered in the content store of all of the routers along that branch. Right? So the data is both delivered to the client, but everybody who's marked in blue has a copy. Client 2 asks for the same data. So its interest propagates up. As soon as it hits a place where the content exists, the interest matches the content store and is sent from that point. So basically you add the branch from the client to where the data already is. So you're making a content distribution network. You're doing it dynamically. It's based on the interest. Right? It's a distribution network that's specialized to that particular set of interests. Data's only going to go where there's interest. You can prove that any piece of data is going to take at most one trip across any given link. Because after it's taken a trip, it's in the downstream content store and it's going to be satisfied out of the content store, so you don't need to pull it across the link again. That's optimal, right? You can't do a delivery network that uses less bandwidth than that. Because in this model, and in most of the models, you're distributing along a source tree, right? There's a root that has the content and it's going out to all the consumers of that content. All of the mass of a tree is at its leaves. Right? You sort of see it in this picture, but it doesn't have to be a binary tree. In general, the nature of a tree is the mass is down at the leaves. What that means is there are lots of copies that get seeded very close to the consumers, which means that the average latency, how far you have to go to get your copy, is very low because the data very rapidly percolates from the root of the tree deeper into it, which means closer to the consumers. And none of these replicas announce the replicas. The fact that we're putting the data in our content store, to be useful, it doesn't require that we say via routing that we've got the data. The way that the data is found is because we're on the path to the source of the data, it's discovered from the routing that defines the distribution tree. This is the same model that's used in things like CBT multicast, core-based trees, that you don't have to put state everywhere. You can have very high-level state, things that defines repositories. That induces trees, which can be then used to control the distribution of replicas and let you use those replicas efficiently. And the efficiency is described there. Minimum bandwidth, minimum latency, minimum link use. So you make a close to optimal CDN with no control traffic automatically. And it's specialized because it's done on each particular data item. The distribution network is specialized per those data items. So we've got an implementation of CCN running. We're planning to do a GPL open source release of it, of the core of it, which is what we've got running, in September. I'm not sure when in September, but it's going to be before the last day of September, this September. The people that do real work are working on it while I'm here enjoying myself. We've done some measurements of that implementation. Here's some data. This is a comparison of the bulk data transfer performance of CCN versus TCP. It's not just a request response protocol. I mean, you can embed TCP IP in it. You would like it to have the same performance. So here we're varying the window size for TCP. That's the x-axis, the pipeline size. And we're verifying the number of simultaneous interests you can have in process for CCN, which is the same parameter, right? How many unsatisfied interests you can have outstanding. And we're varying it from 1 up to about 50. And the numbers there are packets to make them directly comparable. So you can see for TCP, it runs stop and wait when it's only got one packet. It increases linearly as you give it more packets. This is a local test, so there's no transit delay. It's all store and forward delays, which is why that goes up so steeply and why it's really flat, right? It's why it's not round. And then we saturate at the link bandwidth, which is 100 megabit per second. CCN, this is TCP's a kernel level implementation that's been continuously tuned for 20 years. It's pretty good. CCN is a task level implementation, which we've had running for a couple of weeks. It's pretty bad. So the leading edge is really pretty grim there. It's a big pipe because you're going from application into the kernel, out to another application, back into the kernel. You do that 2 times per hop. And so a lot more store and forward delays, a lot more rise time, but it goes up and it flattens out. We get an asymptotic throughput that you can read from the asymptotes the relative efficiency of these protocols. TCP is 11, the app bandwidth, which is what we're displaying here, is 11% down from the link bandwidth. That's the size of the headers, the Ethernet header and the 40 byte TCP IP header. Right? The CCN's encapsulated in UDP, so it's got the same Ethernet and IP headers on it, plus a CCN header. Right? So its bandwidth, it can't do any better than TCP is doing, and it does 23% worth. That's basically the size of the name and the size of the SHA-256. Right? So our name is as big as a TCP header, and our SHA-256 is as big as a TCP header. So we've got exactly twice the overhead. We get to within the overhead, we get the same asymptotic throughput. We saturate the wire. Right? We're running flat. At the wire, we're running 100 megabits per second. We're down 20% in the throughput because it's not an apples for apples comparison. We do security and TCP doesn't. Right? And basically, the factor of 2 difference is the security overhead. Things change a lot if you look at a sharing test. So here we were distributing a video to 4 clients, and a YouTube video, do it via TCP, and you do it via CCN. TCP, and we're doing this over a 10 megabit Ethernet. So it's a bottleneck link, slow bottleneck link. In TCP, each client pulls down a separate copy. So as you add more clients, this is measuring the time until the last guy gets the video. So it's the time to completion for all 4. For TCP, the time to completion goes up linearly as you add the clients because they're all sharing the same bandwidth. And so as you add a new client, you're having the bandwidth for each of the others. For CCN, number of clients doesn't matter because they all share the same, broadcast protocols. They all share the same copy. So irrespective of the number of copies, you get the same performance. I want to say this one last thing about mobility management, and then I'm over my time. So in CCN, the issues of mobility management are very much easier. I mean, they're a reality in the modern world. They're hard to deal with. They're way harder to deal with in IP. The core one, in IP, who you're talking to matters. And so when that changes, you have to somehow paste over the fact that it's changed. And use mobile IP or some other tunneling mechanism to do that. You have to bind a host identity. In CCN, it doesn't matter who you're talking to. It matters who you're talking about. And so if who you're talking to changes, you don't care. You didn't care to begin with. You don't know. So there's a level of mobility management, the session preservation, that simply doesn't exist because you're dealing at the content level, and that's immune to mobility. When I move from here to there, I still want the same stuff. Right? So I just can keep asking. There's another issue of mobility management that has to do with the connection-oriented, you ask for, say, a YouTube video. That's the granularity at which you can request data, and then you get the whole thing. It's because the segmentation is a transport level abstraction, not a network level abstraction. So getting data is all or nothing at very large levels. So when you're pulling down a YouTube video and you move to a different place, the data that's coming towards you, you have to somehow revector to that different place. And you don't want to waste a lot of bandwidth putting it in the wrong place. It constrains the way that you construct tunnels and how dynamically you want to construct tunnels. And you have to predict where you're going to be in order to correctly move the data and not send too much of it to the wrong place. It's because you're dealing with very large units. CCN, the segmentation is done at the lowest level, and you ask for a packet at a time. So it doesn't matter if the original piece of content was 60 gigabytes, you're getting it a kilobyte at a time. And if you're talking to something upstream that says, we've got a 2-packet bandwidth delay product, you give me 1,000 outstanding interests, I'll forward 2, because we've got a 2-packet bandwidth delay product, and you only need 2 to fill the pipe. Right? So you don't have a lot of data that's coming at you. And if you move, you haven't made a very big mistake. And because that data is being cached all along the path, even if it goes to the place where you've been, it also went to the guy upstream of him, and that's a copy that you can get in the new place that you are. Right? You can take advantage of the locality, which means that you can do very efficient mobile distribution being very stupid. You don't have to predict where you are, you don't have to know where you're going, you don't have to know where the infrastructure is, because you're not making a bunch of big mistakes that you then need to fix. And lastly, because you don't have to worry about looping, you can use all your links and you can use them all simultaneously. So if you're trying to figure out of a set of carrier wireless, infrastructure wireless, point-to-point connections, Bluetooth, figure out what works to get a piece of data, the answer is try them all. Something's going to respond. I'm going to see the response because interest and data are always paired. There's no unidirectional communication in CCN. There's always a pairing. So you can try experiments and you can always measure the results. And you can condition your future behavior based on measured results. So the answer for a lot of the mobility management is try it, conditional on policy, like I don't want to charge my 3G link, I don't want to use my 3G link any more than I have to because I have to pay a lot for the sucker, but everything else, try it. If it works, use it. And I will know unambiguously if it works because I can measure it. I send my interest, I get my data. I'm going to skip over this, I hope. Come on, I hate builds. Go away. This is our CCN protocol stack. We take the IP model, as Norbert was saying yesterday, the waste, IP, that narrow waste in the stack, has been tremendously valuable. It let us evolve what's below it and above it in many different dimensions. New services, new applications, create things like the web, create things like VoIP. But there may be other things that are equally as valuable for the waste. We think that little chunks of content in the very specific, what I talked about for CCN content, signed name pieces of data, we think that would be a really appropriate waste for the world as it is today. You need to put two new layers around that. One we call the strategy layer, and it's basically the mobility management layer. It has to be in the stack because the world today is lots of ways to communicate. And you need to figure out dynamically, almost on a packet by packet basis, what's the best way to communicate. And that needs to be in the stack. And your stack needs to be engineered so you can use that information. The other is there needs to be a security layer. I mean, trust is just too important. Provenance is just too important. The network and communication is too much a part of our lives. And that has to be in the stack. And at least the identity part can't be optional. You have to be able to do the signing. Other than that, it looks pretty much like an IP stack. And it's as simple, roughly the same performance, I believe. And with that, I am done, except for questions. I'm over my time. Do we have time? Yeah.
The question in 70 number slides. 70 number slides.
Go back to 70. Let me see if I can figure out how to do it. Wait. This one?
No. Oh, okay. Actually, you told that that is if someone gets the data from one of the nodes that is far away, then another node that is near to this the node that already used the data, this node will be able to take the data very easily from this node. But and last some other slides before you told that is in every node the address of the content is stored. Is this the address of the content or the content itself?
It's the content itself,
yeah,
and its name.
A lot of waste of resource because of wastage of resource. It's the resource. So if you're doing stat muxing, you've got to have a buffer. And all CCN says is there's a smarter way to use that buffer than to use it for queues. It's a memory. Treat it as a memory. Treat it as an addressable entity. We've got the addresses, they're the content names. And so when a packet lands in a buffer, remember that. So
it's no waste of memory. It's the packet landed in that memory, it lands there for IP, it lands there for CCN, right? The buffer has to exist. CCN doesn't require any more buffer than IP does. IP, there's a certain minimum buffer that you have to handle the statistical variation. CCN requires basically the same amount for different reasons, but it's basically the same amount. And you're going to get the data because of the dynamics of the protocol in IP. You have to throw it away. There's no way that you can use it again. And so it ends up being discarded. But it was a valid copy of the data. If the protocol were designed so that you could use it again in IP, you wouldn't put it in a queue. You would save it and you would use it again. But we can't. In CCN, it's designed so that the data is reusable. It's because you address things via data, not via host associations or transient associations like a TCP 5-tuple. And because of that, because of the reuse, same memory, no more is required, but we can use it in a way that facilitates reuse. And that doesn't cost you anything, right? If the data is never reused, you don't pay any more with CCN than you would with TCP, modulo bigger headers, right? So slightly lower efficiency. But CCN is as efficient as TCP for data that's only used once, and if you use more than once, it's exponentially more efficiency, right? The 10 million copies of the New York Times, one trip across the link, so you get huge bandwidth reductions.
Wonderful talk, thank you. My question is the following. I'm trying to understand what kind of assumption you make for the progression of technology for your model to be really adopted and work. So you talked about cheap memory, because you store a lot of information on it. You talked about the progress in hashing, understanding hashing better. Are there other key technologies or key discoveries which you base essentially your model on?
No, we're not even basing it on. If you look through the measurements, if you deploy CCN today with the routers that you have today, it's a win, because you don't. If there's no sharing, right? If the traffic pattern is exactly conversational traffic with no reuse, at worst you pay an additional 10% in the overhead, but you get much higher data integrity. If there's any sharing whatsoever, then you win by the amount of sharing. And for highly replicated content, for things like YouTube, it could be a really big win. So there's a benefit with no technology changes. Likely changes of the technology are cheap memory means you could remember a lot more. That's of no value to IP. In fact, it's a detriment. That can only let you make the queues bigger, but they're already too big. You really want to go the other direction. But with CCN, it's a huge win. It means you could remember more. It means more opportunities for sharing, which means less bandwidth use, because there's a direct trade-off between memory and bandwidth in CCN, not in IP. If you can apply the hashing algorithms in your forwarding decision, you can handle a lot more diversity in the data. So you really need data creation processes that have the same homogeneity as the IP processes, in order to get the same state growth for CCN. That means that content really needs to have repositories at institutions so that you find it one place or a couple places. If you can have a lot more memory available for FIBs, then the content can be at a lot more places. You can start to apply the much more distributed, much more autonomous routing algorithms like small worlds, things that right now are done in peer-to-peer networks, but really inefficiently because they can't take advantage of locality. You can start to use them in CCN, get really good locality, but get lots of autonomy, where content can now be created by individuals and presented by individuals, and you don't have an issue with the state burden of that you have the memory and the scalable lookup algorithms to deal with it. That's a research topic, and this point, all I can do is wave my hands, but I wave them with some confidence that, and would welcome anybody who wants to look in that area. Yes?
It only shows the advantage over CCN over IP. There must be some disadvantage, no?
No.
IP is there.
Oh yeah, I'm not saying get rid of IP. It's a wonderful thing. It's just an incredible engineering achievement, and it's, I think, an unmatched engineering achievement. And we're copying it. We're using as much of it as we can. And you're going to deploy CCN over IP, just like IP was deployed over the telephone network. And Vint never said, I want to replace the telephone network. He wanted to do something new. CCN's something new. It does very well, better than TCP can do.
Yeah, maybe one more question, because then we have to get to lunch. So.
Does the content expire, and if not, other content is stored independently in a node?
I'm sorry, my hearing is very...
Expire.
Oh, yes. So one of the things that was on a slide I had to skip was part of the annotation in a data packet, part of the metadata, is what we call a stale time. And its semantics is that much time after the arrival of the packet, it should be marked stale. There's a bit in the interest, in the CCN selector bit, that says whether or not you will accept stale data. And by default, you don't accept stale data. So what generally happens is the content creator sets a stale time that's defined relative to their production process, right? So New York Times sets a stale time of a few hours. The data goes out. After a few hours, it vanishes from the caches, which causes interest to come up, which solicit new data. Because at most, one interest goes up, irrespective of how many people are asking, right? They all get aggregated as you're going up the source tree, and one piece of data comes down. You don't need to set long stale times to control your incoming traffic for coherence. It doesn't matter how many people are interested, you're going to get one interest per whatever the stale time is. And so it's not a traffic management issue, except in aggregate. And you want to give a good customer experience, you want to let the replicas live as long as they can because they're lower latency if you satisfy from the replicas.
I'm very sorry that I have to sort of cut off the discussion here, but Van will be here tomorrow, so you have another couple of coffee breaks, social event, etc. And also there's a small group discussion with some partners from Forward and Chianti tomorrow after the coffee break, so if you want to join that, please contact me. Okay, so please try to be back as close to 2 o'clock as you can to proceed with the sessions. Thank you.